Hi, it's Dave. Today we're joined with James Douma. He is a machine learning expert, and he's been a frequent guest on my channel. Hi, James. How are you doing?
I'm doing great.
Great.
Great to see you.
Yeah, awesome. We have a James Douma AI playlist, and on that playlist, you'll see a bunch of videos that James and I have done on Tesla full self-driving. It's been a fantastic journey learning kind of the ins and outs of full self-driving. And today we wanted to do a dive into full self-driving hardware. And the question is, A, does Tesla have an advantage with full self-driving hardware? What do their competitors hardware look like, and what does the future of full self-driving hardware entail? So yeah, James, what are your thoughts, I guess, to kind of start out this discussion? I think you had an anecdote or something you wanted to share in the beginning.
Yeah, at the 10,000 foot level, the reason I thought this is an interesting topic, I have a background doing this stuff, and I was looking at this hardware for a while before FSD, before Tesla announced the FSD upgrade hardware, the hardware 3 that's going into the cars. And I thought, I've got all this stuff sitting around. Somebody might find it interesting, so I'll show some of the background work that I did. It also gave me an excuse to catch up on the hardware. I hadn't looked at the competitor hardware in a while. But my anecdote was that I'd been super excited when I found out that Tesla was going to be doing an upgrade for their platform. And I really got into trying to figure out what the upgrade was going to be. Because I'd seen the neural networks. I'd got some neural networks from a hacker friend, and that came out of the car. And I went through this stuff, and I was trying to figure out what would be the right hardware. And then Tesla published these patents that had that. And I had already sort of had this idea that that they would be doing something similar to Google did this TPU chip of their own, which came out a bit before this, and they published this interesting paper on it to show how you could do the architecture of a simple architecture for a calculating engine that was really optimized for doing neural networks, and it would just crush anything else. I mean, it used much less power. It was very simple, and it had just mind-blowing speed. It was 20 times, 50 times, 100 times faster than the competitive solutions that they had, and it was pretty simple. And I was certain that Tesla would do something along these lines. And then they published their patents, and that was super fun because I could take that. I built a model to try to understand just what the architectural parameters would be to optimize their engine for the kinds of neural networks that they were doing. So my girlfriend and I, we were on a road trip, and when Autonomy Day was happening, so we're driving through Tucson, and I'm listening to, I got it running on the phone, and it's sitting in the dashboard, and I'm like, yes, as we're listening to Pete Bannon sing, it's just what are you talking about? For 2 hours, I'm cheering and everything as I'm hearing Pete Bannon and the various people go through the thing. So for me, it was this total victory lap. I felt because I actually. So they did everything that I thought they were going to do, and then they ended up being quite a bit more ambitious, because my expectation was actually that they would do the silicon as an accelerator. And instead of doing a SoC is a system on chip, where you basically do one piece of silicon customized to your solution, and you put everything that's complicated and important on that one piece of silicon. It's the cheapest, it gets you the lowest power. It's the most technically difficult in a lot of ways for the team that makes the part. There's a much easier way to go, which is you buy a SoC, a system on a chip that has a microprocessor and a GPU and memory controllers and all the stuff that kind of everybody wants in their system. And then they could have built a separate chip that was an accelerator. This is what Google did with their TPO, for instance. Google, who's got plenty of IC capability, they did a very unaggressive design for their TPU. It was a 28 nanometer, which is a very conservative processing node for making ICs. They ran at a relatively low clock speed, and they didn't need to get very aggressive with it, because the architectural advantages over GPUs or CPUs or the other ways that stuff were being done are so high that even a relatively conservative design, you don't have to take a lot of risk. It can just be your first try. Will just crush the alternatives for what you can do. And I sort of expected that Tesla would do that. So when I saw that, no, they went to the full-on, the Apple approach, or no, we're going to go with a full custom, a good process node. We're going to put everything in there. That was actually really, I mean, it was exciting to hear. But then after the fact, it was like, oh yeah, this is Elon, right? Like there's not going to be a half measure. He's going to want it to be better, cheaper, faster. He's going to want everything, the whole shebang. And they made it fit inside this really remarkable power envelope. And it's an amazingly clean, straightforward, and really robust design. I was really excited to hear it.
That's cool.
Anyway.
Yeah, I mean, I'm dying to learn more about full self-driving hardware. So one anecdote was I was like at Autonomy Day in the room. It was a bunch of institutional investors, and Pete Bannon goes up there to explain the full self-driving hardware. This is like in April 2019. And he does more of a technical presentation, right, of the whole thing. Yeah. And these guys are not, no one's like technical in the audience. These guys are investors. And I see everyone, they're just like they're like looking at each other. They're saying like, do you understand any of this? Right? And like, I think that guy next to me, he's like, do you know what's going on? And it was so funny because they went technical, and a guy like you who's like into it, who understands it, will understand maybe, you know, the intention and the goal and what they're trying to do. But I think for investors, it went over their head, you know, and myself included, you know, I'm like, I don't know, you know, I know the gist of what they're trying to do. You know, they're trying to put everything together, make a customized solution exactly for their software needs, right? But all of the technical details were way over my head too. But yeah, I'm wanting to know. Yeah, can you help us decode this? Can you help us understand? You know, what Tesla's hardware is all about? Yeah, let's go for it.
If you have questions about Bannon's presentation, I would be super happy to answer them. It was a brilliant presentation. I felt like I was actually like, 15 minutes in the presentation, I was like, oh man, this is a wrong room or whatever the deal is. But I felt like the presentation, it wasn't just for the people who were there, right? Yeah. It's super credible to anybody who knows the tech to listen to this stuff. And I mean, I think Elon said at the end of Bannon's, or maybe most of the way through Bannon's presentation, I was like, you know, this is probably a more technical presentation than most of you were prepared for, and I know it's probably going over a lot of your heads. But we wanted to make it clear, because a lot of people won't believe, that Tesla has made the best chip for full self-driving. Like, why would that happen? You know, it's not something that you would expect, and yet it's true. Mm-hmm. And I think, you know, there's nobody who knows the tech is going to look at this presentation and is going to doubt that it's true. Like there's no competition for this part.
I mean, I don't want to overlap with some of the stuff you have prepared, but maybe I'll just shoot off a couple questions about Pete Bannon's presentation. So I was watching it actually yesterday to kind of get up to speed. Some of the things that they're saying is, first, one of the most important things was power consumption. They wanted to get it under 100 watts. Are they saying basically 100 watts per mile?
No, it's 100. So a watt is a measure of power. It's not a measure of energy. So energy is like a watt hour or a kilowatt hour. That's energy. So that's like what it takes to go someplace. So you would say a certain number of kilowatt hours per mile or something if you were trying to measure it in terms of that. 100 watts is 100 watts. It's 100 watt light bulbs worth of continuous power. So it'll use 100 watts, whether the car is sitting still in traffic or whether it's driving on the freeway, right? So the watt, the watt hours per mile that get used by this car, it'll depend on how fast you're going, because the FSD, it's per unit time, the energy it uses, not per mile. But so a Model 3 uses around 280 watt hours per mile. So if you were driving in so this is 100 watts. So over the course of an hour, it will take 100 watt hours. So it would be, it will use like a quarter of a Model 3, a quarter of a mile of a Model 3's worth of driving energy per hour of usage. So it's quite small compared to the needs of the car. I think Elon had said later in the presentations, because one of the analysts had a question along these lines too about what the usage was, and he suggested that for if you have a Model 3 that's a robotaxi and it's driving around and it's averaging 17 miles an hour in town or something like that, well, if your FSD computer is taking a kilowatt, it's making a dent. It's making a real dent in the amount of range that the vehicle has. I mean, it doesn't destroy it, but it has an impact, right? It affects the economics of the thing. But 100 watts, that's down in the noise, right? Mm. So when you think about power, this is, you kind of have this scale. 100 watts is okay. 1,000 watts is kind of, yeah, that's kind of painful. We really don't want to go there, right? So that just kind of on the scale. They could try to get below 100 watts, right? But it's not really going to make much difference because 100 watts is about in the noise. Right. The pain point starts at 500, 600, 7 watts. At a kilowatt, it's painful. At 5 kilowatts, which is like that's the power consumption for some prototype self-driving cars. That's a non-starter because that's going to hit your range way too much.
Mm-hmm. Okay. So how can we think of what percent, let's say I'm driving my Model 3 for an hour. What percent does the full self-driving computer use, you think, of the energy?
So let's say if you're driving for an hour and you're driving at 17 miles an hour, right? You're going to go 17 miles over that hour, and the full self-driving computer is going to reduce that. You would have gone 17 and a quarter miles, and now you're going 17 miles. It costs you a quarter mile over the course of an hour. So if you're driving 60 miles an hour, it's a difference between going 60 miles and going 60 and a quarter mile, right? Because it's going to be that quarter of a mile per hour, regardless of how fast the car is going. Okay,
that makes sense. So it's pretty negligible, I guess, the energy consumption. Got it.
And you can imagine, like, if it was 10 times higher than that, it would be like 4 miles per hour, right? So if you're robotaxi and you average 15 miles an hour, right? Well, that 4 miles is the difference between 15 miles of range and 11 miles of range, right? Mm-hmm.
Okay.
So it has an impact at that point.
Okay, got it. Pete Bannon also noted that these trillion operations per second, they wanted to get at least 50 trillion operations per second of neural net performance. And then he also said that their hardware was able to process about 2,300 frames per second. I mean, are these correlated? Do you need that much neural net processing in order to process that many frames per second? And then is the 2,300 frames, is that because of the 8 cameras, right? They just matched exactly what the 8 cameras was outputting?
This is a little misleading, the whole frames per second. And if you've got 2 computers and you want to compare them, you can get these sort of artificial synthetic numbers, kind of like trillions of operations per second. But you can have a very high TOPS number and not be able to use most of those depending on the problem that you're trying to solve, right? If the neural network is a really good fit for your hardware, you might get 90% of that number. And I think that is about what Tesla probably gets. They have 145 TOPS, more or less, that the FSD is rated. That's both chips, both of them running, right? So it's a 36.8 for each of the 2 NPUs in one of the FSD chips. And of course, there's 2 of those. So the whole box together ends up being 144. And when they run a neural network, they can run a neural network and spread it across all these chips. So they can use all 144 TOPS. But now say you had a different architecture, like it can also, and like this is one of the reasons they're talking about this is because comparing a GPU, which is not optimized for neural networks, to Tesla's FSD chip, which is optimized for neural networks, you get this kind of strange thing, which is, you get a certain number of TOPS for the GPU and you get a certain number of TOPS for the FSD chip. And of course, say for instance, they're both 144. For instance, you can say, well, the GPU will be about as fast. Actually, the thing is, the GPU ends up not being nearly as fast because GPUs aren't as good at running neural networks. They have a hard time using all 144 of their TOPS. In fact, so Tesla's system is going to be, the FSD chip is going to run at about 95% of the full TOPS rating for the kinds of networks that Tesla runs. Now, if you were running a different kind of neural network, you would get different numbers. Now, Tesla designed this system specifically for the kinds of neural networks they want to run, and they get very high efficiency. But I went back and I did a calculation on the GP106, which is the GPU that they had in the other. That's the GPU they have in this one I was showing you earlier. This is one of the FSD machines, the FSD computers. Sorry, this is not an FSD. This is an AP2 computer The FSD is exactly the same size as this. And this one has a GP106, which is an NVIDIA GPU, which was the accelerator they were using in hardware 2 and hardware 2.5 to do that. So even with the code optimized to run on the GP106, which like the AP2, the neural networks were optimized to run on this box, they could only achieve 45% of the maximum rating. So this is rated at, let's see, is it 612? It's about 6 tops, but they were only able to get 40% of that because the GPU isn't made for processing neural networks. You can get more of those tops on some things. Like if Tesla's neural networks were a lot smaller, they would be able to get a lot more tops. But and I'm going to go through the architectural differences and why the GPUs end up not being quite as good. But so Tesla wants to have a metric that kind of means something to people where they can say, this is what we got on the GPU and this is what we get on our computer. And so what they decided to go with was they took one of their AP1 networks, the main camera network, AP2 networks, that they ran on the GPU and that was already optimized for running on the GPU. And they ran it as fast as they could to get a measure of how fast the GPU was. And they got 110 frames per second. And they took that exact same network and they just put it on their hardware and they got 2,300 frames per second. So that's a very simple way of comparing the relative speed of these two platforms. And this is where they get it's 21 times faster. Now, that network is not the network they run in FSD. And 2,300 frames per second is not very useful, right? Having a frame every 2 milliseconds. But as Pete Bannon explained, another one of the finance people asked him, like, what does that, what does TOPS mean? He described it as it's a currency that you can spend in various kinds of ways. You can either run more neural networks, you can run bigger neural networks, or you can run at higher frame rate. You can trade these things off. But basically, it's a more powerful computer and it allows you to solve harder problems faster. That's the net out of it. Now, for the most part, what Tesla does with this is they run much bigger neural networks. I mean, that's the main thing they want to be able to do. They wanted much more capable neural networks for FSD, and that meant they needed to be bigger than what they could do on the GPU. Does that make sense?
Yeah, generally. Pete Bannon, I guess Elon and Pete Bannon were also talking about how this was 2 years ago, they were already in the middle of developing a next generation chip. And Elon mentioned it would be 3 times, I guess, capable or better. And he actually let it slip that it would be ready probably in 2 years or something, right? So it's almost 2 years. 3 times better, like what would that be used for, the next generation chip? Would it be used for example, getting better resolution? If they could swap out all the upgrade their cameras to better resolution, would that help, you think, with accuracy at all? Or just like how would they just do larger neural nets, or what's your take?
It'd be mainly bigger neural networks. That would be the main thing. So the neural network in AP1, in AP2, the neural networks they're mainly based on this backbone design that came. It was originally developed by Google as part of GoogleNet. It's one of the reasons that's a very attractive architecture to go with is it's very computationally efficient. That is, for the number of operations that your neural network does, or rather for the size of the computer that you're running, if you're running real time, you can get higher accuracy. It takes longer to train, and it has certain other restrictions but when they were running on the GPU, they needed a very efficient way of running neural networks, and they did that. On FSD, looking at the FSD networks, they still use those inception backbones. This GoogleNet, they called the general architecture the inception architecture, and the original one was GoogleNet, which is sometimes called Inception V1, and there's a V2, 3, 4. They further developed it. But Tesla had just been using the basic Inception backbone. They still use some of that, but now they can run other things that are less efficient because they've got a lot more compute power, so they don't have to be so laser focused on running as efficiently as possible. So that's one of the things they get from having more power, is they get more flexibility in the networks they choose. Another thing that they can do is they can run a lot of networks in shadow mode if they want, because they don't need all of the compute power all the time to drive the car. They can be testing out other ways of doing things in shadow mode in cars that are driving around without having to compromise on the performance of the vehicle itself. So they get a lot from having a faster computer in terms of flexibility. And I think that's a key thing. Now, as they narrow down the way that they want to do stuff, and they figure out exactly how various aspects of the problem need to be done, they may go to bigger and bigger networks, because the bigger a network you put on, all other things being equal, a bigger network can give you better accuracy. There's a diminishing returns kind of thing. So there's kind of this knee of the curve that you want to aim for, which is a good trade-off between, the amount of data that you need, the amount of training that you have to do, the accuracy you get, the speed of your computer, and all that kind of stuff. But as there's a good chance that in the future there will be situations where they would like to have more processing power, and so a subsequent generation of the FSD chip would enable them to, once again, inside the same box, get significantly more power. I'll be surprised if they only have 3x improvement by the time they come out with the chip.
Do you think if there is that next generation chip coming out, who knows when, I would imagine the next year or so, but would it be a drop-in replacement? You think the whole module, the full self-driving computer, just same size, everything, power, just
like hardware 3. I mean, it looks a little bit different from hardware 2 externally, but the connectors are basically exactly the same. The box is the same size. You pop out if you have a Model 3 or a Model S, there's the cover inside the glove box pops out, and it's just bolted there, and it has a bunch of connectors. So you take some screws off, plug it in. On the Model 3, it's a little more complicated because they use liquid cooling. So they have to drain the coolant out of the car when they swap it. But the Model S and the Model X, it's air cooled. And you can, somebody who's got good practice can swap it out in 10 minutes or something like that. It's really easy.
Yeah, I mean, that's great news. Like I have a December 2017 Model 3, and it's got the, full self-driving, right? 3 hardware 3. For the next generation chip, how do you see this rolling out? Do you think Tesla will charge an upgrade to get the computer, like my car, or do you think they'll just swap it out?
So it's good that they have a follow-on chip in the pipe, right? I think Elon commented recently that they don't need it yet. And I think, when they decided to do this, you don't know exactly what the future looks like, because these technologies are all developing really rapidly. Nobody knows exactly like what the perfect shape of the network is, what's the perfect amount of data to do something. And I think that their ability to use all the processing power of the FSD chip has not grown as fast as they feared it might. The thing is, you could have imagined a situation where they got FSD kind of working, and, in Karpathy's group, they're training the neural networks and that kind of stuff. And at some point they're like, oh, we need to go bigger, bigger, bigger on the neural network. And then they could have gotten to a point where they're like, we're almost there. If only we had more power, right? If we had twice as much power, that would just put us over the curve. And so you want to have that chip waiting in the wings in case that's how things work out, because that's 2 years, 3 years in the future at the time they were designing this chip. So it's good to have it. But I think that the reality of what has happened is that the autopilot team has found that there's lots of room for improvement without making the neural networks bigger. And so they haven't, they've got more than enough power to do the stuff they want to do right now. So pushing the chip out doesn't get you anything if you can't use it. Like if they can't use all the power in the system that they have right now, and they don't think they're going to use it in the next year, there's no point in developing that box or rolling it out to the fleet or anything. Because if you wait a year, you can make an even better chip, right? Like every year that you wait, the chip that you can make when you roll it out is going to be that much better. So when Elon was talking about getting a 3x speed up, one thing that they don't deal with, that nobody who does the first generation sort of tensor processing multiplier. Nobody ever does sparsity. So sparsity is this thing where neural network is basically, you have this sort of interconnect grid. I don't know, can you see this screen over here?
Yeah, let's go for it.
I think I have, let's see, NN flowchart. So this is the flowchart that Steve Bannon showed when he was talking about, this is what a neural network does, is you have some input. So the input, this is a flow down chart. So the input comes at the top and it goes down. And so each one of these boxes is basically a giant matrix multiply operation. So you have an input, in this case, it would be like a camera frame, which has been normalized and whatnot. And then you do, these are convolutional neural networks that they use. And so they do these, each neuron has an input field, which would be 3 by 3 or 5 by 5 pixels or something like that. And it has a set of weights where it looks at for instance, the red channel and the red, green, and blue channels, and it has a weight that it applies to each one of those. So it applies those basically it takes all the red pixels, and each one of the red pixels has a number that you multiply it by, and then you sum them all up. And then the green pixels all have a number you multiply it by, and you sum all those. And if the total of the weights times the pixels that you're applying them to exceed a threshold, then the neuron outputs a value. And if it's below a certain threshold, it basically outputs a 0. That's what a ReLU is. So there's basically a very large number of these neurons that are basically applying weights to various subsets of pixels inside these images. And the output of this convolution operation would be a big stack of the outputs from probably 1 million neurons or something in this. So they'll have like 1 million neurons connected to this initial image. Each neuron has its own set of weights and whatnot. And you process all this stuff and you get a set of activations, which is like what came out of that layer of neurons. Then you do it again. You have another convolution on top of that. There's other operations you can do, which is pooling, where you basically do operations between neurons in a layer instead of to the outputs of the previous layer. This whole flow chart is just basically convolutions with ReLUs on the output of them, where each one of these is an enormous mathematical operation. It will be taking megabytes of input and doing a giant matrix operation on it, and it will be generating megabytes of output. So the flow chart itself is very simple. Like if you look at a flow chart for a graphics program or any kind of modern program, the flow charts would be way more complicated than this, because these are individual instructions. Each one of these blocks is one instruction for the neural processing engine. It has a pointer to a giant input array, it has a pointer to a set of weights, and has a pointer to where it puts its output. And it just cranks on this huge amount of number crunching and then squirts out this kind of crystallized block of updates from the previous layer. You work your way through these layers one at a time. And when you get to the end, kind of magically, you have, a box that shows you where all the cars are in the picture, or whatever the deal is. And the magic of neural networks is that using a technique called backpropagation, you can figure out what's the combination of weights for all these neurons that gives me the output I want from the input that I have. Mm-hmm. So what the neural processing unit in the FSD chip does is it does these blocks, and it does them really efficiently.
Okay, so I want to pause here for a second, because I think this is like some of the crux of how FSD or neural nets work. So you've got this, the input. So the input is basically the frame or the video, right. The images coming through the neural networks.
A single frame from a video.
Yeah. Okay. And it's getting through into the first layer of neurons or nodes. And then it's analyzing like different set of pixels, right? I guess are they just groups of pixels, you think, like 3 by 3 or 5 by 5 pixels?
So in a convolutional network, each neuron in the input layer has what's called an input field, which is, for these kinds of images. It'll be a square input field. It'll be 3 by 3 or 5 by 5. So for instance, if you've got your big rectangular image, right, and you take, a 3 by 3 square of pixels in the upper left corner, and you have a set of weights. So 3 by 3 is 9, right? And then you've got 3 channels, red, green, and blue, if they're RGB. Actually, so Tesla uses YUV, color space, but they still have 3 layers. So that neuron's output, it looks at the red, green, and blue channels for each of those 3 by 3 pixels. So it's got 27 numbers coming in. And for each one of those 27 numbers, it has a weight that it has learned, that it has been trained through this training process. So it multiplies those together and it sums all the outputs out. So each pixel gets a multiply and an add, because you're accumulating the results of all those. Then the neuron has a threshold. If you multiply all those weights by those pixel values, and you sum them all together, you'll have some threshold. Say it's 0. Say if the sum of all those, because the values can be positive or negative. If the sum of all those is less than 0, then that neuron outputs a 0. And if the sum of them is more than 0, then you put out a number which is more than 0. This is what a ReLU does. A ReLU is the nonlinearity that gets applied to the output of if you don't have a nonlinearity, a neural network is just it's a simple linear operation, and having multiple layers doesn't have any advantage. You have to put a nonlinearity in so that a neural network can learn complex functions.
Okay, so
that's a little bit side.
So taking a step back, so this image is going through the first layer, and you've got all these neurons, I guess, analyzing different portions of the image. Do they overlap as well?
They do.
They do.
So so I described like one neuron that you have that's looking at a 3 by 3 field. So in a convolutional neural network, you take that neuron. You've got an identical neuron next to it that looks at, so you've got pixels 0, 1, 2 by 0, 1, 2 in the array. So the next time you play it to 1, 2, 3 by 0, 1, 2, so that you're still on the first 3 rows of the image, but you move over 1 pixel, right? And you've got another identical neuron with the same weights. Because the thing is, for the most part, features in an image mean the same thing, even if they're slightly moved, right? So a car is a car in an image. If I move a little to the left and a little down, it's still a car, right? So the set of operations you want to do is it's independent of position. A car could be anywhere in the frame. And so we're taking essentially the same set operations. Now, we don't just have one neuron. What that one neuron does is it extracts one feature. It's looking for one particular thing, a particular neuron. So a particular neuron, it might be, say, looking for a diagonal line, which is light on one side and dark on another. And so in that case, you have a set of weights that gives you where that neuron activates if it sees a diagonal line, or you might have one for curve, or one for where it's red and not green, or where it's lighter and darker. So that first 3 by 3 group of pixels up in the corner, it doesn't get one neuron applied to it. It gets a whole bunch.
Got it.
So you might have 128 different features that you're looking at, and you look for those 128 features on every 3 by 3 grid in the entire input. So at the lowest level, the features are very simple things like shades and edges and that kind of stuff. So after that first layer of neurons, you have a set of features that you at this really low level. So now you put another layer of neurons on top of it. And so that layer has, like, for instance, maybe you have a feature for diagonal lines this way and another neuron that detects diagonal lines that way. So in the next layer, you can look for crossed lines, right? Because it can say, it can look at the neuron that looks for these diagonals and the neuron that looks for these diagonals. And as you work your way up the stack, the neurons look for more and more complicated things. So eventually at the high end, you might have neurons like, this is a person's face, this is a cat, this is a headlight, and that sort of thing. Because you get to more and more abstract layers as you go up. And eventually when you get to the top, you have neurons, which is, this is a car, this is a truck, this is a stop sign, and so on, right?
So with the neurons further down, I guess toward the end, would they be analyzing larger groups of pixels in order to get, like, this is a face, this is a car?
So as we mentioned before, the convolutional neurons, they have an input field which is wider than 1 pixel. It's one neuron, but it's looking a little to the left and a little to the right. So each time you go up a layer, the input field basically expands. So a given neuron in the first layer, it can only be affected by things that are that are a pixel to the left, a pixel to the right, or right underneath it. But if you go up another layer and you have another 3x3, now that one can be looking across 9 pixels by 9 pixels, right? Because it's got the input from a group of 3 pixel, from a 3x3 grid of neurons, which each has a 3x3 grid as an input, right? You go up to the next layer and its input field is even larger because it's a grid of 3x3 of the previous layer, and so on. Once you get about halfway up the stack of the neural network, you start getting neurons which can have a value that can reflect something that could occur anywhere in their input field. Right. And of course, when you get to the very top of the neural network, you've had multiple layers of neurons that are mixing and matching things about the image that could have occurred anywhere inside the image, like grass or trees or whatever that thing is. So you might, if you've got your tree neuron and you have your grass neuron and you have your sky neuron, you might decide it's a certain kind of landscape. And so that you could have a neuron above that that says this is a certain kind of landscape. Mm-hmm. It's not a desert. Yeah. So the desert neuron doesn't fire if you have grass. So.
Yeah. Okay. So to summarize this, so you've got, the image coming in. The first layer of neurons is basically looking for pretty simple stuff, shades, like, edges, maybe, a line or something. And then it outputs value greater than 0 if there is some type of resemblance of what they're looking for.
If it finds the feature that it's looking for.
Okay, exactly.
Within its space.
Yeah. And so a weight greater than 0 means there's some confidence. Like the higher the weight is, closer to 1, it'd be much more confident, right?
You could think of it that way.
Okay. And then the next layer of neurons basically looks at a bigger space. They're looking at the previous layer, but more. They're able to do, and then they're looking for more complex things, not just, one line, but maybe 2 lines, or maybe like a triangle shape or something, and then this continues to go on with each layer, adding more complexity, looking for more complex things until, the end layer of neurons is able to pick up the car, the cat, whatever, very, confidently based upon all of the previous neurons' work and their weightings, mm-hmm. right? And then, the next step then is the training, which is you back propagate it. In the sense that you have the result, and if it's correct, then it's like, okay, that gave you the right result. But if it wasn't correct, if that cat wasn't a cat, it was a dog or something, then you could tell the neural network their mistake, that the output was something mm-hmm. different, and they can go back and correct all the weights, I guess.
So back come propagation.
Up with
that. So one of the restrictions of neural networks is they have to be differentiable, which means that you don't have discontinuous functions anywhere inside it. Everything everything is a smooth transition. So every value that a neural network makes a transition between, it slowly transitions through all the values in between. And that lets you do this very important trick, which is, if you get to the output and you know that you wanted a particular output, and what you see from the neural network is not that output, it's a little bit different. If all of the layers are differentiable, you can do a thing where back propagation, it calculates exactly how much every single weight contributed to the error to the output. So for instance, say that I have a dog. We talked about the dog and cat pictures before, and it told me cat when it was a dog. So I can back propagation lets me look at every single weight in the neural network and see what direction and how much would that weight have to change in order for the output to become dog instead of cat, if it gave me the wrong value. And then you don't actually flip all the values all the way there, because we want the thing to learn to generalize across lots of images. So what we do is you look at if I went this far, it would flip the image output from dog to cat. So I'm going to go 1/1000th of that distance. I'm just going to nudge them all slightly in the direction of dog from cat if it was wrong. And if it was cat, and it should have been 100% cat, but it only told me 70% cat, I'll nudge it even more in the direction of cat. So the amazing thing about backpropagation is if assuming that the neural network has a reasonable structure and is capable of learning this, you show it 1,000 pictures of dogs and cats, and it learns to generalize the difference between dogs and cats. And while in that earlier description I was talking about, for instance, the first layer would be edges, and the second layer might be crosses, and the third one might be circles, and so on. As a human, we don't actually have to figure that out. If you have a neural network and it's got enough layers to solve the problem, and we figure out if it's got enough by building a small one and trying it, and if it doesn't work, we make it a little bigger, right? Until you find a network that works. We make them bigger, we make them wider, we add more neurons, more different kinds of kernels and features, and you just expand it until it can do the job that you want it to do. And when you do this backpropagation process, the neural network itself, it decides where to put the circle neuron and where to put the cat neuron and at what level to put the edges, and every single detail of every single neuron in the thing, it just figures out on its own. We don't have to design anything aside from we have to make sure the network is big enough that it can do the problem. And if it's big enough that it can do the problem, and I give it a reasonable amount of data to learn the thing, it'll learn to give you the answer that you want.
I mean, but we need to create the neuron, right? The actual what it's looking for in that image. Is that correct?
So nothing is handmade in this. It's the one today. The shapes of the networks, for instance, how many neurons, when we were talking about you have the first layer at the bottom that the image comes into. And, I have to decide, do I want my input field for my neurons to be 3x3 or 5x5 or 4x4? How big do I want it to be? So that's an input that you decide on. And another one is, well, how many do I want in that thing? Do I want 32 features in that first layer? Do I want to look for 16? I'm using binary numbers because this is the conventional thing. So, you might have 4 features, you might have 8, 16, 32, something like that. And when you look at these networks, typically you'll see they're rounded off to the nearest binary number because those are computationally efficient. It's almost never going to be the case that in the best of all possible worlds, it would be exactly 64. But for most of the neural networks you get about the same performance at 64 as you get at 65 and 66, right? But if you go to 128, that makes a big difference. So, so the kind of rule of thumb is you just go in these binary increments. So maybe I have 32 features, and that's another parameter that basically describes the shape of my network. Then what's in the second layer? Frequently you want to narrow the field. So, if your input image is 1,000 by 1,000 pixels, after you do a certain amount of consolidation and processing, you can reduce it to 500 by 500 pixels as you work your way up. So typically you have more and more features you look for, but you narrow down the input field as you work your way up to the top also, because it's easier to process. It's more computationally efficient. And it turns out if you stay 1,000 by 1,000 all the way up the network, you don't necessarily get better performance than if you go from 1,000 to 500 to 250 and so on. And this latter case runs a lot faster. It's good enough, and it takes a lot less computation. So that's the way they tend to get built. Got it. So a human being basically decides, what's the input field? How many features do I want? And then how many layers do I want to stack? That's the human input. After that, the human decides, what output do I want? And you have to decide how you're going to phrase that. For instance, the way that it specifies, say, if I want to build a neural network that tells me, oh, there's a car in this image, and here's where it is. Well, how do I do the where it is thing? And the convention is we put a bounding box around it. We ask the neural network to say, it's in this square. Mm-hmm. And the way that we do that is we have it tell us this is the top left corner and this is the bottom right corner. So we can draw a box if we know what those two things are. So the neurons at the top of the output, I basically have these images, which are where each one of them is either the top left or the bottom right corner of an object or nothing, right? And if it's the top left or that, what that lets me do is I get an output where I can figure out what the bounding boxes are for every single object inside that. So that's a bounding box output, and Tesla's neural networks, they generate bounding box outputs. Actually, they do a slightly better thing where they generate cuboid outputs now, where if you have I don't know if you've seen the pictures of in the FSD displays and whatnot, you'll see like a 3-dimensional truck, and it'll have like a cube, not just a 2D box, but a cube drawn around it. So they'll actually have a layer that guesses the 2 opposite cuboid corners, and then they can draw that box in 3 dimensions around the object, which basically says, here's this object, it's at this location in space relative to the car.
Mm-hmm. Got it. So when the image is going through all of these layers of the neural net, like let's say from start to finish, let's say just one image, right? First off, do you know what resolution is it? Is it like, HD quality?
Yeah, so the input images they take a 1280 by 960 input image, and they flip it into a YUV color space, and they down res the U and V layers. So the illumination layer stays 1280 by 960, and the other 2 layers go to 640 by 480. Mm-hmm. So they do the initial pass that they do on the intensity layer, or the illuminance, I guess it's called, the Y layer. This one really is looking for edges, and they're easier to see in illuminance, and that has a strong effect. But it turns out, in retrospect, that the U and V layers, they're not nearly as sensitive to illumination. And that first layer going in, because it's the biggest one, you got to lower and lower neuron widths and heights for the images as you go up. So that first layer is really expensive. So Tesla, they absolutely minimize the size of that layer by doing illuminance at the full 1280 by 960, and then they do the U and V layers at 640 by 480. They'll stack those 2. Then they downsize the illuminance, and then they blend the 2, right? Okay. So then the output above that is 640 by 480. And as they work their way up, it'll go from 640 by 480 to 320 by 240 to 160 by 120. They will very quickly narrow the input field as they work their way up. Then they'll do a lot of processing at maybe, they'll come all the way down to like 40 by 30 or something like that. Oh, wow. Then when they want to create the bounding box layer, they go wide again. And so the bounding box layer will be like 320 by 240 kind of scale. Mm-hmm. And it'll have a sort of reduced resolution set of bounding boxes that it produces for all the objects that come out.
Okay. So from start to finish, just one frame, how many, what's the computation processes? What the number of, is just to give a random, do you have any, idea?
Let me, I have a really precise number, actually. But let's see if I have, I don't know if I have okay. So, I mean, the first version of FSD that I got to look at has like 100 neural networks in it. They vary a lot in size, but so the biggest one takes 20 milliseconds to process. 27. I think is right. And then a lot of them process an input to an output in like 2 milliseconds. And the different networks they're extracting different kinds of features. So that's the biggest networks are around 5,000 instructions, a bit less than that. And the smallest ones might be 10 or something like that.
Okay. So in terms of, for example, Tesla gave their FSD 3 hardware 3 does 144 tops or trillion operations per second. What percent do you think is required to run FSD right now for Tesla in terms of operations per second? Is are they using just a small portion? They
use 100% of the computation.
Really?
Now so I mentioned this. Initially, I looked at this and I'm like, wow, they're using the whole thing. And then an acquaintance, I think it was actually Very Green, pointed this out to me. It's like, why would you leave anything on the table, right? Like, say, for instance, that you only need half, right? Instead of letting the other half go to waste, you run something in shadow mode, or you put a bigger network in because you can, or whatever. It's going to it's got that processing capability. You might as well use it for something. There's almost always some useful thing you can do with it. So you just keep loading stuff into it to use whatever thing is. I think the analogy he used is that like in modern computers, there's never free DRAM. Like you look at the operating system, because free DRAM is just being wasted. You can always buffer something or use it as a cache. I mean, it's got some kind of value to some kind of process. So, you know, if you look at the memory usage on your laptop, it almost always says 100% is being used. And you're like, God, I'm only running a web browser. Why is it using 100% of the memory? It's like, well, you know, it's just caching stuff, or it's got a file buffer or something, right? And so that's essentially what the FSD machine is doing right now. Is that, you know, Tesla, they've got it. They use 100% of it because they've got all these little things they could do on the side that have some value.
Mm-hmm. Wow, awesome. So what I wanted to hear is, I think this was a cool just introduction into kind of the beginnings of Tesla's full self-driving, but also, or their hardware, but also kind of how the neural nets work and, you know, why it needs kind of hardware that is really optimized and can handle all this, you know, power. And so what I want to do is I want to cut this video right here for part 1 of the FSD hardware. And then part 2 will go into, I know you prepared kind of a breakdown of, can you explain kind of what you, I know you prepared some, a look into the competition
talk
as
a
well,
little
right?
about, yeah. I'm just going to do a comparison between like an NVIDIA GPU. So NVIDIA has a platform drive AGX that it's kind of like the development platform that they have available for developing self-driving stuff. And I was going to walk through that and sort of compare and contrast the two.
Okay, awesome. Yeah. I mean, this topic is so crazy, fascinating to me. So yeah, we'll go ahead and we'll do part 2 at that. And I'm sure I'll have a lot of questions and you'll have some cool stuff to say about it. So we'll go ahead and end part 1 here, and then we'll see everyone else who's watching. Hopefully you'll stay for part 2 in the next video. All right, thanks.